chemical buffer is a solution that will resist changes in pH when acid or base is added to that solution. Your body contains many buffers. In the fluids in your body, you want to maintain a relatively constant pH. If you eat a lemon or a tablespoon of baking soda or something, I can't think of a basic food off the top of my head, but if you eat something basic or acidic, you don't want that to alter your blood pH, because the enzymes in your blood are designed to run at within a very specific window of pH. Now, how do you make a buffer? Well, a buffer is a combination of a weak acid with its conjugate base in the same solution. So acetic acid and acetate can be a buffer. Hydrogen carbonate, ion, and carbonic acid can be a buffer as well. Now, why do they work? Here are two buffers in your body: the dihydrogen phosphate, hydrogen phosphate ion system, and hydrogen carbonate and carbonic acid system. And they're very effective if you add 1 milliliter of 10 molar HCl to blood plasma, which is buffered. The pH will drop by 0.2 pH units. If you do it to saline solution, which is unbuffered, right, it's just salt water, it will drop to a pH of 2. So how does a buffer work? Well, if we consider the dihydrogen phosphate, hydrogen phosphate ion buffer system, if you add a strong acid, the basic form of the buffer is going to react with it. And when you add the strong acid, which contains hydronium, the basic form reacts, and when it does so, it produces a weak acid. So you take the strong acid that you add, and essentially you convert it into a weak acid and water. And because this strong acid reacts to produce a weak acid, the pH doesn't go down very much. If you added a strong base, hydroxide, the hydroxide would react with the acid form of the buffer, react to produce a weak base, and as a result the pH wouldn't go up very much. You can also explain a buffer using Le Chatelier's principle. So this would be a reaction that's happening inside the buffer here. This should be an equilibrium arrow. So let's put a double-sided equilibrium arrow on this guy. If you were to add hydronium to this solution, what would happen? Well, if you add hydronium, that means you're adding a product, so you would cause the equilibrium position to shift to the left, and as the position shifts to the left, the hydronium would be consumed, producing this weak acid, which again doesn't cause very much of a change, right? Doesn't cause the pH to go down very much. If you added hydroxide, what's that going to do? And you might initially look and say, well, that's not going to do anything because there's no hydroxide in here. But you have to remember that hydroxide and hydronium will react with each other to neutralize. And when they do so, that means that when you react with the hydronium, it's going to consume the hydronium. So the amount of hydronium is going to decrease. At the same time, when they react, they'll produce water. So the amount of water is going to increase. And the net effect of both of those things is going to be that the equilibrium position is going to shift to the right to replace the hydronium that's been lost. So it will cause a shift to the right, and as it does so, we've consumed the hydroxide and we're reacting to produce some of this weak base. So we take the strong base and we turn it into a weak base. And so we can explain it this way, or we can explain it the way that we did first. In both cases, the buffer is able to react with either the strong acid or the strong base that we had and consume them, producing a weak acid or a weak base in turn.